All right, so we have this formula for capacitance, right? That it is equal to the dielectric constant kappa multiplied by epsilon naught, the vacuum permittivity, multiplied by the area of the plates divided by the distance between the plates. Right? This is on your formula sheet. Great. What I'd like to do is similar to the idea of the rule for resistance, that rho times L over A, and how that interprets or helps us understand the rules for adding resistors in series and adding resistors in parallel, that we're changing the length or changing the area. I'd like to do that the same for talking about capacitors. Now, you can talk about capacitors in terms of their effective or equivalent capacitance the same way that you can talk about resistors in series or parallel, their equivalent resistance. And there's a way to do that using the rules for voltage and charge and things like that, which I'll link to some videos for that too, and it's in your textbook. But I think another helpful approach to it, not more or less helpful, is taking a look at this relationship too and seeing what it means for us. If I have three capacitors that are wired up in parallel with each other, then what we're doing is we're going to see, like, what is the equivalent capacitance? If I were to replace these three capacitors with one capacitor, how would it compare to the originals? Well, if we take a look, then we know that the voltage across each is going to be the same, and we can talk about charge and build up and everything. But I like to think about this equation here, because what I'm doing is I'm taking three different areas, A1, A2, and A3, and I'm really, if I'm putting them side by side, I'm adding them up. And so the total area, or the equivalent area, is going to be A1 plus A2 plus A3. Right? And so if we make the assumption that the distances and the dielectrics are the same, and you don't have to make that assumption, but we could model them that way, it makes it nice and easy. But this assumption is true, that the areas are the same. And so what we would find out then is the equivalent resistance is going to be the kappa epsilon naught over d, which we are for the same, we're modeling them as the same this way. We don't actually have to have different areas. You could have three different values of capacitance that have the same area, but have different values of d or kappa or whatever. But I like modeling them this way because I think it's helpful for understanding what's going on. It gives me an intuitive understanding. If I just have like a set value for thickness and a set value for dielectric, then I'm changing the area as I change capacitance. And it's a good way of modeling that, and the rules work out nicely for that. So if I would do that, then the equivalent resistance would be my kappa epsilon naught equivalent resistance divided by distance. But this is simply going to be the kappa epsilon naught A1 plus A2 plus A3 all over distance. And that, if we distribute out that kappa epsilon naught and the distance, is equal to C1 plus C2 plus C3. And so our series capacitors is equal to the sum of our individual capacitors. Sorry, this is not series, this is parallel. I can add. So parallel resistance, the parallel capacitance is equal to the sum of our individual capacitors. And this is exactly opposite to the rule for resistors. Because in resistors, if you have them in parallel, you're adding an area, but remember for resistors, area was in the denominator. And so what we're doing is we're then decreasing the overall resistance. But for capacitors, area is in the numerator, and so if we're adding up areas next to each other, then we're going to be adding up capacitance. And so the parallel capacitors are going to be added up this way. Now let's see what we do for series capacitors. If I have capacitors in series, and for this model, I'll just assume that they are lined up like this. I have C1, C2, C3, and they have separation distance D1, D2, and D3. Okay? Now, it doesn't really matter if I have any connection between these capacitors. It would work the same as if I shrunk them down so one plate was exactly touching the back of one plate was touching the front side of the other plate. I could actually shorten these wires down without affecting the overall thing to be essentially one capacitor that has a total separation distance of D equivalent, our overall separation distance D equivalent, which would be equal to the three separation distances. And I think you can see where I'm going here. That if I were to say, what's the equivalent resistance here? Well, my equivalent resistance would be kappa epsilon naught A over my equivalent distance, which is going to be equal to kappa epsilon naught A over d1 plus d2 plus d3. Okay? And it's fairly easy to show then that if I were to take a reciprocal, a cross multiply, or whatever, what I end up with is that 1 over my equivalent resistance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Essentially the same rule for adding resistors in parallel, that the length, or the area is getting bigger, and so they add up. That way the areas add up, which means that the resistance is going to go down according to that rule. Here, the distance, which is in the denominator, is adding up, which means that the capacitance is going to go down and decrease. We can store less energy here for the same amount of voltage. And so what that means is that for series capacitors, 1 over series, it's going to be equal to the sum of 1 over the individual capacitances. And the same rule applies for parallel resistors. This is for series capacitors. So capacitors and resistors behave differently in circuits, and they add up in exactly opposite ways than you might expect. All right, for those who really want to see it. If we started with this, then what we can do is we can take the inverse of both sides. So 1 over the equivalent capacitance is going to be d1 plus d2 plus d3 over kappa epsilon naught times A. Since I have a common denominator here, I can actually split up my numerator, and I get 1 over my equivalent capacitance is d1 over kappa epsilon naught A plus d2 over kappa epsilon naught A plus d3 over kappa epsilon naught A. That's right. This is 1 over C1, 1 over C2, 1 over C3, and so we get 1 over my equivalent capacitance is 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance